and welcome to episode number 13 of CS350 online. On today's episode, we will continue our discussion of virtual memory, of course starting with reviewing the virtual memory implementations we discussed last week and then moving on to some improvements upon them. But first, of course, the OS of the day. This is not CS360. All right. Our OS of the day is called OpenVMS, and this was an operating system which has been around since 1977. It was produced by DEC, also known as Digital, and it has had many names throughout its life, starting out as names like Star or Starlint and VAX 11 VMS and VAX VMS. The VMS in OpenVMS usually stands for Virtual Memory System, which is something that they were priding themselves on at that particular moment in time. Now, this operating system is actually a very interesting one because it's actually still around and is still under active development. It features all of the things you would anticipate a modern day operating system to have, such as time sharing and batch processing. But kind of like the PIC operating system, this also does transaction processing as well. So it has some database functionality built right into the operating system, which has its advantages, especially if you are an operating system operating on large company servers, which is essentially what this OS was really meant for. That being said, there was actually a desktop version of it with a GUI, but that didn't really take off terribly well. Now, this operating system offered many other features, such as supporting TCP/IP for networking, but also DEC's own version of network protocols, DECnet. It had a distributed file system, which is pretty cool for the time, and it had versioning, security, many other things. What is really interesting about OpenVMS, though, is its stability. So if you think of the operating system that's sitting in front of you right now, and it's probably going to be one of macOS, Windows, Linux, iOS, or Android, and most people don't have OSs outside of those few at the moment. How many days can you go before the operating system asks you to do an update and reboot the computer? How many days can you go before your operating system has a blue screen of death and forces you to reboot? Now, admittedly, operating systems are significantly better today than they were 10, 20 years ago, but OpenVMS is even better. There have been installations of OpenVMS which have successfully run without any kind of reboot or fault for more than 10 years. And I can't think of a single Linux, Windows, or macOS machine that could run and stay on successfully for that period of time. So this is a very stable operating system used only today in the highest of high-end servers and quite rare. It's really only been developed for Intel Itanium right now. But it's fun, it's cool. And this is not the logo anymore. This is the old logo when it was Digital. Digital was acquired by HP, and the new OpenVMS logo is nowhere near as cool, so I didn't bother putting it here. All right. So let's talk about where we left off. So last day, we started discussing virtual memory, which is a new topic, and I'm just going to go back here in the slides. So we were discussing what is virtual memory to start with. And if you remember, we've done all of this work at abstracting the user program from physical things. So what we want to do is we want to separate the user from the actual physical hardware. We want to separate the user from the actual kernel. Part of that we haven't done is separate the user from the memory. And that's what virtual memory is going to do. It's going to abstract physical memory in such a way that programs themselves are not even aware that the memory addresses that they're using are artificial in nature. And at the same time, this kind of isolation, what it's going to give us is each program believes it's the king of the world. That is, it's the only program in existence, because all programs will now use this exact same range of addresses. So, I mean, for fake addresses, not real addresses. And because each program uses the exact same set of addresses, programs are going to be effectively isolated from each other, because I can't suddenly access dead beef in another process, because dead beef is in my process. So if I try to access dead beef on my dead beef, it's going to be dead beef in me, not dead beef in somebody else. All right. So with that discussion, we gave a little brief example showing you how multiple processes running even on a modern machine, there's proof that this is going on. I opened 3 copies of the same program, and I showed you where the code and the heap and the stack segments were in those 3 address spaces. And it looked like the address spaces all overlapped each other. Now, some of you might have noticed, if you go back to episode number 12, that even though it looks like the address spaces as a whole overlap, the actual stack segments didn't technically overlap in the virtual address range. And you might have thought that was pretty peculiar. Why doesn't the stack segment live at the exact same address in each of the processes? This is something that modern operating systems do to kind of obfuscate a little bit how data is being stored in the address space itself. They do what's known as address space layout randomization. So that means every time you create a new address space and you're creating the stack segment within that address space, we have a general region of the address space where we want that stack to live, but where the actual start of the stack is going to be randomized a little bit. And the same with the code and the same with the data. Now, OS 161 and many simpler operating systems don't do this, and every code, data, and stack segment will live at the exact same spot. But modern operating systems do this address space layout randomization. It's kind of just to make it a little bit harder to, reverse engineer things by inspecting memory and so on. All right. So there are several goals we have towards virtual memory implementations. Number 1, of course, virtual memory needs to provide us with protection, that is isolation from other processes. It has to also be it has to be such that the process is not aware that this is going on. We have to not just isolate the processes from each other, but the process can't even be aware that the addresses it has aren't real. And the most important part as well is going to be efficiency, because the CPU is not aware these addresses are fake. And so there's going to need to be some mechanism responsible for translating each of these fake addresses into a real address. And since every single instruction is going to require at least one address translation, and that is the program counter, since the code lives in a virtual address, we are going to need to actually do at least one translation per instruction. And in a lot of cases, with loads and stores, you're looking at 2 and maybe even more. So we could use the kernel to do this, but that would be very inefficient. Instead, we use hardware. We use the MMU, which is on board the CPU to do that translation. But in order for it to do its translation, it actually needs to be a fairly simple translation. So we need to be efficient in terms of time, but also in terms of space. Time, how long does it actually take to compute that translation? And space, how much extra memory do we need in order to perform that translation? Now, we introduced you to 2 separate schemes for doing virtual memory last in episode 12, and that was we looked at dynamic relocation, which is very simple. We've made the assumption that the address space in virtual memory is a contiguous block. That is, it's not laid out in any particular way, or if it is, we're not going to care about that. So we have one contiguous block that is the address space, and we're going to find some matching contiguous block inside of physical memory, and we're simply going to map this contiguous block to that contiguous block. So we're going to map this 28 kilobytes here to this light purple block down here, and this yellow block up here that's 48 kilobytes gets mapped to this contiguous block of physical memory. And then for each process, we keep track of 2 integer values, One is the offset, so where in physical memory does that block start, and also what is the limit, what is the length. And then the address translation is blissfully simple. All you need to do is you are going to compare the virtual address to the limit. If it's less than the limit, then it's in the address space, and we simply add the contents of the relocation register, and you're done. If, of course, the virtual address is greater or equal to the limit, then we're going to throw an exception, not an error, an exception. Now, a lot of people ask every term, why is it greater than or equal to and not just greater than the limit? Remember that in CS we start counting at 0. So if our array holds 10 elements, we can't index at element 10 unless it's MATLAB. MATLAB starts counting at 1. Every other language in CS pretty much starts counting at 0. So the valid array indexes are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, not 10. And the same is true for memory. So L, the limit, is not a part of the address space. Now, the problem, of course, with dynamic relocation was that our address spaces are not a contiguous allocation. There are large blocks of empty space in between each of the regions of the address space that we actually use. So this is actually the address space for sort in OS 161. And what you'll note here is you've got the code segment in purple up at the front. Then with some space between it, you've got the data segment in yellow. And then in this kind of winey color, we have our stack. And they're separated really far apart. Now, to do this with dynamic relocation, we actually have to allocate 2 gigabytes of space, which is from address 0 all the way to the bottom of our stack start. So that is actually 2 gigabytes. And that ends up resulting in a lot of internal fragmentation because we've got potentially gigabytes of space inside the address space that my process isn't going to use, and yet it's been allocated, so it's completely wasted. And the downside, of course, is if our address spaces were contiguous, then we have external fragmentation because each allocation would be different size. So while dynamic relocation was really, really fast, really, really efficient, it's not really a good idea, which is why we introduced segmentation. Now, segmentation is very similar to dynamic relocation when it comes to what the math that's involved. And what we're simply going to do is we're going to only keep track of the regions of the address space we're actually using. Conveniently, address spaces, there is like a code segment, maybe a globals, a heap, and a stack. There's not many regions in an address space. So you're looking at a small handful of blocks that we're going to keep track of. And then we're going to do contiguous allocations for each of those individual blocks. So in these processes here, we've got 2 segments per process. So we're going to find a contiguous block of physical memory for segment 0 and a contiguous block of physical memory to map segment 1 to. And then for each of the segments, we keep track of their offset and limit. So once we know which segment it is, we're going to do the same dynamic relocation that we did before. The only difference here is that we actually need to figure out, given any virtual address, which segment is it a part of. And how you figure out the segment number is you count how many segments are there in the address space. We're going to use the highest order bits of the virtual address to represent the segment number. So you count the number of segments there are, you take the log, base 2 of course, of that number, and it will tell you how many bits you need to represent the segment number. You extract those highest order bits from the front of the address, and that's your segment number. And then the MMU is going to actually use the relocation and limit for that particular segment that it has extracted to actually do the translations. And we did an example of the translation math in episode 12, so I'm not going to go over that again. One last thing to point out is there are several approaches for the MMU for segmentation. One approach is that the MMU actually has a relocation and limit register for every segment of the address space. That's really impractical because that could be a lot of registers on the MMU, and registers actually aren't free. They take up physical space. We generally want our hardware components to be as small as possible. The other downside is that we don't actually need just 2 registers per segment. We actually need more than that because we need to keep track of whether certain segments are read-only and so on and so forth. There are properties to the segments. And so instead of getting 2 registers, it might be 3 or 4. So it actually spirals out of control really quickly and makes the MMU really big. So what you'll actually see implemented more often is an MMU that has just 2 registers, one that has a count of how many segments this current process is using, which actually gives us a lot more flexibility in our operating system for how segmentation is implemented. And then the second register on the MMU has a pointer to a table in physical memory that actually has the relocation and limits and any flags for each of the segments, and the index will be the segment number. So this here is the segment table approach is much more realistic than our other one. All right, so that's kind of where we left off. Now I'd like to go and talk about paging. Now I know we got started on this last day, but there was a weekend in there, and I know everybody forgets things. So we noticed the fact that segmentation actually solved our problem of internal fragmentation, purely because now we're only actually allocating space for the regions of the address space we're using. The problem, however, is that we still suffer from external fragmentation. And in order to get rid of external fragmentation, we need to actually have every allocation be exactly the same size. So as I mentioned in episode 12, what we're going to do is we divide physical memory into these equal size frames. And the most common frame size you'll see is 4 kilobytes. And we're going to do the same thing with virtual memory. We're going to subdivide all of virtual memory into equal size pages. And it's important to note that the page size is equal to the frame size, or this doesn't really work out that well. It's not that it can't be made to work, it's just, it's pain. All right. Then the magic that happens here to get rid of external fragmentation is instead of requiring a contiguous block of 28 kilobytes to store process A's address space in physical memory, we are instead going to require 7 frames of physical memory. And those frames don't have to be contiguous. They can be anywhere, which means that if there's some space over here, I can put 1 frame over here. And if there's some space over here, I'll put a frame over here. And I can have some here and here. So we're going to take the pages of virtual memory and we're going to map them to whichever frames we can find that are free. And because each request is the same size, we only run out of memory when we actually run out of physical memory. So we've gotten rid of external fragmentation. We haven't gotten rid of internal fragmentation, but it's not really worth talking about because the amount of memory you would waste internally is very small, very, very small, because effectively you only allocate pages if you actually are going to write to them. So since the pages are so small, per page you might be and it's going to be on a segment basis, per segment of the address space, you might waste 2 or 3 kilobytes. If you think about how much RAM computers have today, wasting maybe 6 or 7 kilobytes per process really doesn't matter. Now, of course, address translation for this particular method is going to be rather complicated. And in fact, we're going to need to take what we did for segmentation and take it to an extreme. So what we're going to need to do is we're going to need to create what's known as a page table for every process. Now the page table lives in the kernel's memory, which means it's going to live for the entire, well, so long as the process is alive, the kernel will keep track of this page table. And what the page table contains is a mapping from the page number to the frame number. And it also contains a little bit of information to indicate whether or not the page is used. Now, I'm going to switch over to OneNote here in a minute because I'd like to explain why that is. In this particular example here, our address space was contiguous 28 kilobytes. And so we only used 7 entries of our page table, and the remaining, however, 9 of them are not in use. Okay. But this isn't how address spaces are laid out. People always ask, why do you need a page table entry for every page of virtual memory, regardless of whether you're using it? Why do you need the valid bit? So let's go over here and let's actually draw this out. So here I've got OneNote, and let's actually draw an address space. Actually, you know what? Let's do a grid because that'll make it a lot easier to draw. Maybe. So here I have this is my address space. And inside the address space, I have my code segment. And I'm going to use the grid lines here, and I'm not sure if you can see the grid lines terribly well. But let's suppose that my code segment uses 2 pages. And my data segment, remember there's always space between these. Let's say my data segment uses 3 pages. And let's say that my stack segment right now is using 2 pages. Okay. So this is my range of virtual addresses. This is, for the moment, 0. And I'm going to use a 32-bit virtual address space because that just makes life easier. So this is my virtual address range. These colored blocks represent my 3 segments within the address space. Again, virtual. If I try to create the page table for this, though, I need some way to indicate that these pages here are not used in my address space. So in my page table, I need to indicate used, not used, used, and so on. Which means that our page table has to contain an entry for every possible page of virtual memory, regardless of whether we are using it in the address space or not. Because that's what this valid bit is for. The valid bit is going to indicate whether or not this particular page is being used by the address space or not. Now, how do you determine the number of pages in the address space? Well, that's not too bad to do. The number of pages of virtual memory is equal to the VM size, that's how much virtual memory you have, divided by the page size. That's how many pages you would have of virtual memory. And you can similarly take this formula and you can compute how many frames of physical memory you have. So in our example in the slides, our virtual memory size is 2 to the power of 16, and our page size is 2 to the power of 12. By the way, this is 64 kilobytes divided by 4 kilobytes, if you're wondering. And the answer is, of course, going to be the number of pages we have is 2 to the 4, or 16. So there you go. We have 16 pages of virtual memory in our address spaces. All right. So, OneNote has some serious bugs in it. I create a new page and, okay, there we go. All right. So looking back then here, what you're seeing is that we have our page table with 16 entries, and for our index is going to be our page number, and it's going to map to a frame number, and then we use the valid bits to indicate whether it's in use or not. You will note that to compute the number of page table entries is the same, the formula is here at the bottom. The number of page table entries in a page table is going to be the same as the number of pages of virtual memory. But that isn't discussing how we actually do the address translation. So the address translation, well, first off, you have to keep in mind, in order to do the address translation, we need to know to which page does this virtual address belong. So what we're going to do is we have each virtual address actually has two parts, just like with segmentation. Sorry, I'm trying to bring one note back up. So our virtual addresses actually have two parts. The first part is the page number. So the highest order bits of any virtual address are going to be the page number. And then the remaining bits are going to be the page offset. So that's the address within the page. So effectively what's going to be happening is the MMU is going to split off the page number. When we get the page number, we use to index the page table. So our MMU gets the page number stripped off. It uses that number to index the page table. It gets the page table entry. So PTE for page table entry gives us a frame number and it gives us the valid bit. Now that the MMU has the page table entry for this page, it's going to check valid. So we check the valid bit. If we are not valid, the MMU is going to throw, of course, an exception. Otherwise, we're going to translate the address. Now, how do you perform this translation? Well, you're going to take the frame number you get from the page table entry in the formula at the bottom of the slide, and you're going to multiply it by the frame size, which is equivalent to multiplying it by the page size, and then you're going to add the offset, which is the page offset, the remainder of the virtual address. Now, how do you get the frame or the page number then? Well, the page number is the virtual address divided by the page size, and the page offset is going to be the virtual address modulo the page size. And this is usually where I say, on an exam, without a calculator, do you want to do division in modulo without a calculator? Of course, the answer is no. But you don't have physical exams where you're in person in a room and it smells of fear and, the pack. We don't have that this term, which is actually kind of nice, right? So you're going to be able to do an open book with calculator quiz. That being said, nobody still wants to do division and modulo with a hex. So there's another way to do this address translation without doing all of this division and modulo stuff. How are we going to do that? Well, it's pretty simple. Let's take a look at our virtual addresses. Remember how I said that the virtual address has two components. The highest order bits are the page number, and the lower order bits are going to be the page offset. Well, if you look at the format of the physical address, it's also the same thing. You've got the highest order bits are the frame number, and the lowest order bits are the frame offset. Now let's look at this diagram here. We strip off the page number and use that to look up in the page table, which gives us the frame number, which we simply drop down into the highest order bits of the physical address. Then we take the remaining bits, which are our page offset, and we just drop them right down into the physical address. And that's it. So if you look at this from this pictorial representation, the address translation is actually quite simple. But you're not quite ready to do it. You need a little bit of information first. You need to know how many bits for the page offset. You need to know how many bits for the page number. and you need to know how many bits for the frame number. Now, the number of bits you need for the offset, be it the page offset or the frame offset, is going to be the same because the page and frame offset is the same because the page and frame size is the same. So to get the size of your page offset, in bits, you take the log of the page size. And of course, these are all base 2 logs. So in a 4 kilobyte page, that's 2 to the power of 12, we have 12 bits for the page offset. That's fairly easy. Now, what's harder is figuring out how many bits you need for the page number. To figure out the number of bits you need for the page number, you actually need to know what is the total number of pages or page table entries that would be needed for this virtual memory. So you're going to take the maximum size of virtual memory, which in this case is 2 to the 16, and we're going to divide it by the page size, which is 2 to the 12. So for this example here, we get that the number of page table entries is 2 to the 4. Now that in itself doesn't tell us the page number, but we need that value to figure out how many bits we need for the page number. So to figure out how many bits you need for the page number, you take the log base 2 of the number of page table entries. And you're done. So in this particular example, we have 2 to the power of 4 page table entries, so the number of bits I need for my page number is 4. Now, how do you figure this out for physical memory? Well, I note that my physical memory is 2 to the power of 18. I divide that by 2 to the power of 12, which is the size of my frame. That's going to give me 2 to the power of 6. And so that's how many total frames of physical memory I have, which means I take the log of 2 to the 6 to tell me how many bits I need for my frame number, which of course gives me 6 bits. Computing division and multiplication and logs on powers of 2 is significantly easier than trying to do division and modulo with a bunch of hex. So it's my recommendation that you use this method. All right, so that's not so bad. So let's take a few minutes and actually do some translations here. All right, so I'm going to open OneNote back up again. Let's do that. And again, I'm only going to do this for process A, and I'd like to encourage you to do it for process B on your own, and you're welcome to share the answers on Piazza. So let's do this then. So just giving us a little space to scroll down. Let's start with our first address. The first address we have is 0x102C. Now let's note this. We are using 16-bit virtual addresses and 18-bit physical addresses. We know from the previous slide that our page number is the highest order 4 bits. Now, bits is not hex digits. This address here is actually going to be in binary, something like 0001 000. Let's see if I can remember C. This is probably not the case. So it's 1, that's E. So that's F. D. I think this is C. I could be wrong. I don't usually convert hex to binary on the fly. All right. So when we're talking about the highest order bits to get the page number, we're not referring to the hex. We're referring to the binary. Now, that means that our page number is the highest order 4 bits, which is these 4 bits here. Interesting thing to note is that each hex digit is actually 4 bits. So if your page number is a multiple of 4, you can actually just grab the highest order hex digits that correspond to it. So in this case, it works out quite lovely. So our page number is 1. And you can say 0x1 or you can say 1, it doesn't really matter. Our page offset is whatever is left. So our offset in this case is going to be these 12 bits here. So that's going to correspond to 0x02c. So I'm going to go to my page table and I look at page table entry for page 1. And that gives me frame 26 and that is valid. So I can perform this translation and my translated address is going to end up being 2602C. So that's not so bad, is it? It's actually quite straightforward. Now let's look at the next address. So our next address is 0x9800. So our page number, again, is going to be the highest order 4 bits. Now remember, each hex digit is 4 bits. So conveniently, our page number in this one is going to be 9. So in this case, my page number is 0x9 and my page offset is going to be 800. Now I look up page 9 and you'll notice it's in this ... part and I realize page 9, when I grab this entry from the table as my being a human MMU, I realize the valid bit is 0. So this one is actually an exception because the page is not valid. All right, now let's do our last address here for process A. Again, I'm going to let you do process B on your own as some practice. So our last address is 0024. And I'd like to point out that this is actually equivalent to 24. You are completely within your right to drop the highest order zeros because they're just placeholders. I mean, we don't write for 100. You could write 00100. That's still 100. It's just written really weird. That doesn't mean the zeros aren't there, though. So in this case, our page number, of course, is going to be the 0. So our page number 0 and our offset is then going to be 24. So I look up frame 0 and that gives me F. And it's a valid page, so I just drop the offset right in. And there you go. So that is how we do the address translation for what's known as single or simple paging. Now, we're missing some details here. And those details are kind of important. One of those things is we haven't given any kind of indication as to whether these pages are read-only or read-write. And that's actually really important because your code segment of your address space and your read-only constants should not be able to be written to. How are you going to protect that memory if the hardware is not aware that that memory should be protected? So what we need to do is, in addition to indicating in our page table entry the frame number and the valid bit, we also need some bits to keep track of whether this is a read-only page or not. So we'll have a write protection bit of some nature. We also, and this is going to come into play at the very end of this section, we like to keep track of whether we have used entries in a page table. Because we want to keep track, this is for caches and such, we want to know when was the last time this page was used. We might have something called a dirty bit. And a dirty bit is something where it's like, we want to know, has anyone modified this page? Now, this is not a bit that we use in particular in this course, but it is used in modern operating systems when they do process forks. In modern operating systems like Linux, when you do a process fork, it doesn't actually create a complete separate address space from the parent. Now, I know that's probably going to seem a little weird, but the problem is you've got two identical processes. If they're running the same program, why create another replica of the code? Why not just have one copy of the code and one copy of the read-only. So some operating systems will do that. The problem, of course, is that if the two processes start executing different things and they start doing different things with their global variables and their stack variables, you don't want changes in one process to affect the other process. So we use the dirty bit to detect a write in the one process, which will cause the other process to get that part of the address space separated out. So it's kind of a neat mechanism. But the point I'm trying to make is, in order to facilitate things like usage tracking, read-only, when are things being written to, we have all kinds of other bits that we'd like to include in a page table entry. And they're very useful. But we have a bit of a problem. So let's talk about, we've talked about this concept of calculating how many page table entries there are. But how big is that page table going to be? Now, in our previous slides, it seems really, really tiny because we have 16 pages. We've got 16 entries in the page table. That doesn't seem that big. Who cares? It's been a really long time since we had 16-bit virtual addresses. If memory serves me, Windows 3.1 was the end of that 16-bit era. It's also my favorite Windows. So if you're hearing vibrations, which you may or may not, it's a drill. So here's the problem. So address spaces have grown. We don't even use 32 bits anymore. The last time I used 32 bits on a computer for like the operating system or the hardware was the early 2000s. So we've been using 64-bit systems for a very, very long time. How big is the page table on these systems? Well, how big the page table isn't how many entries there are. I mean, it's related to how many entries are, but it's also related to how big is each entry. So to compute the actual amount of physical space a page table needs, you need to know how many pages are there and how big is each of those page table entries. So we know that the number of pages, or the number of page table entries, is going to be the maximum virtual memory size divided by the page size. So we're going to take that number, which in our case is 16, and we fill it in up here. And then the size of our page table entry, which we're never going to ask you to compute, we'll always give it to you. We are going to assume, let's say, 32 bits for each page table entry. So then for our page tables, we end up, when you multiply those two together, we get a page table size of 64 bytes. And, in all things considered, who cares? It's 64 bytes. But we don't use 16-bit virtual addresses. If we used 32-bit virtual addresses, and our page table entry size remained at 32 bits, i.e. 4 bytes, then our page table would be 4 megabytes. You know what? That doesn't seem that bad to me. But we don't use 32-bit virtual addresses, do we? If you look at most modern computers, they actually use 48-bit virtual addresses. So if we have 48-bit virtual addresses and we have 32-bit page table entries, then my page table size is 2 to the power of 38 bytes. My page table per process would be 256 gigabytes. And that's supposed to live in physical memory for the entire duration of the process. And every process would have that page table of that size. That doesn't work. I don't have 256 gigs of RAM. I waited and waited until Apple came out with this laptop here, which has 32 gigs of RAM, and I considered myself lucky. The machine behind me, which occasionally you might hear rattling, it's got a bad bearing in the fan. That machine, which is my research machine, has 64 gigabytes of RAM. So if page tables, if we use this single level paging implementation as shown here, we couldn't even hold one page table in memory. Page tables can get really big. how are we going to fix that? Well, we will talk about that after a brief commercial break.
How much do you think this advanced operating environment is worth? Wait just 1 minute before you answer. Watch as Windows integrates Lotus 123 with Miami Vice. Now we can take this Ferrari and paste it right into Windows Right. Now how much do you think Microsoft Windows is worth? Don't answer. Wait until you see Windows Right and Windows Paint and to listen to what else you get at no extra charge. The MS-DOS Executive, an appointment calendar, a card file, a notepad, a clock, a control panel, a terminal, a print spooler, RAM driver, and can you believe it? Reversi. That's right. All these features in Reversi, all for just, how much did you guess? 500? 1,000? Even more? No, it's just $99. That's right. It's $99. It's an incredible value, but it's true. It's Windows from Microsoft. Order today. P.O. Box 286 DOS, except in Nebraska.
I couldn't resist. That was too much fun. All right, so how are we going to solve this page tables being too large problem? Well, we don't need to look at that slide. Let's look at your computer. Let's talk about your organization of your files for a moment. When you were younger, when you were downloading things off the internet, you probably weren't thinking about where am I putting the things that I download. So you just download and download and download and download. And maybe all of the things that you downloaded went onto your desktop. I think the worst desktop I've ever seen in my life scrolled for like 4 or 5 pages. It was insane. Everything was on it. It was impossible to find anything. Or maybe you had like just one download folder where you put everything in it and you just operate completely out of your download folder. Well, that's going to get really messy and really ugly. And how do you solve that problem? Well, with organization. You might add some folders in. And maybe you'll do it by letter. So you'll have a folder for all the files that start with A and one for all the files that start with B and so on and so forth. And then you'll put all the files that start with A into the folder labeled A. And then inside of A, if you've still got a million files, you might further subdivide it into files whose second character is A and whose second character is B, and so on and so forth. You're going to create a hierarchy of organization to make it so that you can find the files that you actually have. And you don't create folders if there's nothing that could go into it. For example, on my computer, I don't have any romantic comedy films. Just don't have them. I don't like them. So why would I create a folder for them? That makes no sense. What we are going to do is we are going to do the exact same idea with our virtual memory. We are going to arrange our page table into a hierarchy, a tree. And we're only going to create the branches of the tree that actually have valid pages within them. And what's going to end up happening is we're going to end up, ideally, for most modern day uses, we will end up with a page table that is smaller, but also contains a higher percentage of valid entries. And here's a little example here. So we've got an n-level table. And the idea is we only create a table at a level if there's at least one entry that is valid within it. And what's interesting about this is anything other than the leaves of this table, instead of having page to frame mappings, contained page to table mappings. And only the leaves of this tree are going to contain the actual page to frame mappings. So let's look at an example of this. So here we've got our example from the previous slides where we've got single level paging. And with our single level table, we have 16 entries. And for process A, 7 of those 16 entries are valid, so 9 of them are invalid. That's not too bad. And then we have our 2 levels. So let's say we arbitrarily just divided this table into 2 levels. So what I'm going to do is I'm going to say, okay, these 4 entries, you are now mapping to this entry here. That's table 1. And then the next 4 entries are going to map to table 2. And then the next 4 entries would be table 3 and table 4. But tables 3 and 4 contain no valid entries, so there's no point in creating them because they're 100% invalid. So where table 2, or table 3 and table 4 would be, well, I guess table 2 and table 3, counting from 0, of course. Instead of, since we didn't create the subtables, the leaves for those, because there's nothing valid in them, we're just going to, in our directory, we're going to mark them as invalid. And then we only create the leaves for these tables here, which actually have valid entries. And then we put in our directory, our root, we put a pointer with a valid to that table and a pointer to the other table. So the 2-level table for this same address space here has a total of 12 entries. So this one has 16 with single level. With 2-level, we only have only 12. So we've actually reduced the size of the table. Furthermore, if you look at how many valid entries are in the 2, this one had 7 out of 16. And the 2-level has 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12. So the percentage of valid entries is significantly higher with 2-level paging. It's pretty cool, right? How does that affect our address translation? Well, interestingly enough, it doesn't actually impact the final translation. Once you have the frame number, the translation mechanism is exactly the same. There's no change. You take the frame number, you multiply it by the frame or the page size, and you add the offset. That stays the same because the offset isn't going to change either. The offset is related to the page size only, and that doesn't change here. The only difference is how do you get that page number, that frame number? Well, instead of dividing the address into 2 parts, page number, page offset, now we have to divide it into 3 parts. Page number 1, page number 2, page offset. Okay. And then what we're going to do is we start with the highest order bits, which are going to be the root of our hierarchical tree. And we're going to use those bits to look up the next table in our tree. So I have page 1. So I look it up in the root of my tree, and it's going to say, okay, this is a valid number, and here is the address to the next level table. So then I take the next 2 bits, and I use them to index the next table. And since the next table is the leaf, then I get the frame number and I perform the translation as normal. So we're just taking an extra hop. Now, in order to get our frame number, we actually have to traverse a tree. Traverse the tree using the page numbers to figure out which node we go to next. And that's it. It's actually that simple. Okay. And we can extend this, by the way, beyond 2 levels. I use 2 levels in his example. But essentially what you have is this n-part address, where the first parts of your address are your page numbers, and the last part is going to be the page offset. And you're simply going to peel off one at a time the page number. You are going to look up in that level of the page table that we're currently at, that entry. You check the valid bit. If the valid bit is false, then what you're going to do is throw an exception and stop. It's not a valid address. If, however, the valid bit is 1, then you'll get a pointer to the next table, and then you would pull down the next page number. And you just keep going until you get to a leaf and you get your frame number, and then you can do your translation if the whole process has been valid along the way. It's a lot of extra steps, but it's less memory. Now the question becomes, how many levels do we need? This is an interesting thing. We say in the notes, ideally each table would fit on a single page. Why? Well, this isn't going to make complete sense until the very end of this module. But there's this concept called on-demand paging. And the whole goal of on-demand paging is we want to be able to have more processes running than what our physical memory could technically support. Or we want to have the ability to have a process with an address space who's technically got a bigger address space than I have physical memory for. The only way that you can do that is by doing address space loading on demand. So we only load the components of the address space at the exact point that we need them, which means that our address space lives on disk. Now, disk operations are orders of magnitude slower than physical memory operations because they are further away from the CPU. Because if you're talking about pulling something off a hard drive, you actually have motors that have to spin up. Motors are very slow. So when you want to pull data from a disk, you want to do it in one operation. So usually we set the page size of our memory to correspond to the block size of our disk, or to be smaller than the block size of the disk, because we want to minimize the number of disk operations we do. So for these purposes, which we'll discuss a little bit later on, it is ideal if each page table fits on a single page. What I'm saying is each node of the tree should fit on a single page or less, because that's going to really improve our performance when we do this on-demand paging thing, because we'll have less disk operations. So it's very easy to see that even a single level with our example in the notes fits on a single page. There was actually no need to split it into two. But we need some way of figuring out how to compute how many levels we actually need for the page table. And this is tricky, because if you look at the notes and you're scrolling ahead, you're like, wait a minute, it doesn't show me any formulas. It just gives me an example. I will give you the formulas here shortly. But let me show you one way, and maybe this one example here that's in the notes that maybe will help you see how these formulas I'm about to give you were derived. So let's suppose we used 40-bit virtual addresses. So we have 2 to the power of 40 bytes of memory. And we'll use a traditional 4 kilobyte page size, and our PTE size will be 4 bytes. That's 32 bits. So to figure out the number of pages of virtual memory, we take 2 to the 40, we divide it by 2 to the 12, we get 2 to the power of 28 pages. So that's how many pages of virtual memory there are. That's also how many page table entries we need to support this virtual memory. So now we need to figure out, if we have this goal that every page table entry each table is going to fit on a single page, we need to figure out how many page table entries can fit on a page. Well, the number of page table entries that can fit on a page is the page size divided by the size of a page table entry. So we can fit 2 to the power of 10. That means that we need 2 to the power, now that we know how many page table entries fit on a page, we can figure out, based on how many pages we have, how many page tables do we need. So we take the number of pages, we divide it by the number of entries that can fit on a page, and we see we have 2 to the power of 18 tables. Which means if this was a 2-level table, our directory would have to hold 2 to the power of 18 entries. But that doesn't work, because that would be bigger than a page, so we're actually going to need more than 2 levels. And then what we would do, of course, is if we would divide this again by 2 to the 8, and we would realize that we needed actually 3 levels, not 2 for this. But there's an easier way to do this. So let's go over here. And let's talk about some of the formulas we actually need in order to do this. And I'm just going to make sure I've got my list up here because I don't want to miss any of these very important formulas. They are very, very important. So, just to refresh, the number of bits for the page offset is equal to the log of the page size. So I'm going to call this number of offset just for easy purposes. Then we need to know how many page table entries fit on a page. So number of PTEs on a page is equal to page size divided by the PTE size. And remember that the PTE size is always given. We're not going to ask you to compute that. All right. Now, we've got the number of page table entries that fit on the page. We need to know then how many bits do we need for a page number. That is going to be the log of the number of page table entries on the page. So, I'll come back through and I'll do this with our example. We now have all of the information we need in order to compute our number of levels. So the number of levels is going to be equal to the number of bits we use for virtual memory minus the number of bits we needed for the offset divided by the number of bits we need for the page number. Now, of course, this is going to give you a fraction, so we take the ceiling of this. Ta-da! And if you're having a hard time seeing how this equation works, if we actually draw this out, what this equation does is we're going to take off the offset bits here. We're going to ignore them, and then we're just going to take chunks. Here's the 1 page bits, page bits, page bits. We're just counting how many times you can do that. Now, you will note that sometimes we are left with fewer bits. That's okay, because it's okay to have a table smaller than a page, which would need less bits to address it, but it's not okay to have a page table bigger than a page. All right, so from our example in the notes here, we have a 40-bit. So let's do this in blue. So the number of, I meant to say offset. So our offset bits is equal to the log of 2 to the 12, which is 12 bits for our offset in our example. And then we've got the number of PTEs per page, That's going to be 2 to the 12 divided by 2 to the 2, which gives me 2 to the 10. And then the number of bits per page number is equal to the log of 2 to the 10. So that's going to be 10 bits per page number, which means for the example in our notes with 40-bit virtual memory, the number of levels is equal to the ceiling of 40 minus 12 divided by 10, which is equal to ceiling 28 over 10 equals 3. So there you go. There are the magical formulas that you're going to need in order to determine how many levels you need for multi-level paging. Okay. So, before we go, there's one thing I'd like to open up for you. If you go to the handouts archive that I posted on the Piazza, the extra sample problems, I'd like you to open up one called paging.pdf. Here we go. So this problem here is going to ask you, it's going to give you a setup for a virtual memory system. It's going to tell you the page size, and it gives you a bit of a page table here. And it wants to know things like how many entries are in page table, how many entries are valid, and translate these physical addresses. So that's paging.pdf. Take a few moments between today and Thursday and see if you can try that. And then the other one I'd like you to try is one called multi-paging. You now have all of the information that you need in order to do multi-paging as well. So open up multi-level paging. It's got, again, a setup. This one is 64-bit addresses. And it's got a bunch of questions about how many levels you need. And then the most fun one, my favorite part of this question, is the last part, which is how many valid entries and how many tables exist at each of those levels. So there's 2 sample problem pages for you to try. There's paging.pdf and multipaging.pdf, and they are both in that archive that's posted. So please do take some time before the next episode and actually give them a try. Good sample problems. And to help you out with this, I'm also going to post a virtual memory guide that has all of the formulas that you will need along with examples to do these pages. And yes, when we talk about open book quizzes, that is a perfectly valid book to have access to. All right. Now, back to our slides. That's not the slides. There we go. So you have everything you need to do multi-level paging. There's some interesting questions that we can ask. Is multi-level paging always going to produce a smaller total page table size than single-level paging? It's a good question. The answer is no. It doesn't. Think of it this way. Let's suppose you have a virtual memory and an address space such that it actually uses every single page of virtual memory. So every page is valid. If we were using 48 bits for our virtual memory, then I would need all 256 gigabytes of space to actually keep track of those page table mappings. It's totally valid. If, however, I were to create a multi-level table, I would, in addition to having all those page to frame mappings for every single page, I would have all of the tables for all of the levels that fell above it. Which means there is a point at which single level paging is more space efficient than multi-level paging. And if you are really, really bored, you can try to figure out what that point is. It's kind of a fun 240, 341-esque problem. All right. Where are we going to go from here? Well, before we get on to the next kind of section of virtual memory, just kind of a summary of where we have been before we move on. And that is, let's keep track of what is the kernel doing and what is the hardware doing. So the MMU is responsible for only two things. The hardware is responsible for translating the virtual address, and the hardware is responsible for raising exceptions whenever it cannot translate. So whenever the valid bit is 0, whenever you have an invalid segment number, whenever the virtual address is greater than or equal to the limit. The MMU raises exceptions and performs the translations. The kernel does everything else. So the kernel is going to create and manage the page tables. The kernel is going to allocate and free the actual physical memory. The kernel handles all of the exceptions raised by the MMU, and the kernel is also responsible for updating the registers on the MMU every time we actually change processes. Because of course every process is going to need to have those values changed because each process uses going to translate to different regions. So the kernel does a lot of work, but it doesn't do that work very often, whereas the MMU does a little work, but it does it very frequently. All right, it is, according to my clock, 10:43. So I'm going to say that is the end of episode 13 for today. On our next episode, we are going to start the discussion of TLBs, which is a very special cache that we use to improve the performance of our MMU. We're also going to start talking about how virtual memory is implemented in OS 161. So super exciting stuff coming up next on episode 14. And I will see you on Thursday.
In the beginning, the people who worked with computers were considered magicians. Abracadabra! But digital took the mystery out of computers. Digital Equipment Corporation pioneered the mini-computer, making compact, easy-to-use systems that can grow with your business. From your independent digital supplier, you can get hardware and software from one source without any hocus-pocus. Digital, we took the mystery out of computers.